Okay, welcome everybody to the third day of the Beyond the Boolean Cube workshop. So our first speaker today is Nima Anari, and he's going to talk about discrete sampling via continuous random walk. So take it away, Nima.
All right. Thank you, Dor. Thank you for the invitation. Happy to be here. So the title of this talk is, as you can see, Parallel Discrete Sampling via Continuous Walks. This is a joint work with Yizhi, Tianyu, June, Brian, and Katherine. And June, yeah. So if the title seems vague to you, this is the title that seems easier to remember, Dolly for spanning trees. So let me explain a little bit. The goal of this talk is to introduce some sampling algorithms. And actually the algorithm is based on the thing that Dolly uses to generate images. Everybody here knows about Dolly, right? So these are Dolly is a model by OpenAI that you type in some text, it generates an image for you. And the process it uses to generate that image is a sampling process. So very cartoonistically, it starts with some pure noise, and it's over many steps, it denoises it to something that looks like a good image. Okay. This process is actually very well known in the theory community by another name called stochastic localization. So these are formally the two same processes. So the goal of this talk is, in the theory community, this has been mostly used as an analysis tool, whereas in diffusion models, you use it as an algorithm to sample. So the goal of this talk is to give you some new algorithmic applications of stochastic localization. All right, so let me give you a brief primer on sampling. So the sampling community, actually, people usually divide themselves based on whether they work on continuous sampling or discrete sampling. So in the continuous world, you have some distribution on Rn, you want to sample from it. Here, there is really one good tractable class, similar to how in optimization, there's one good tractable class convex functions. In the continuous world, distributions whose density is log-concave, log of the density is concave, is the tractable class. So slightly even better, similar to well-conditioned convexity, you can also have well-conditioned log-concavity. This is when it's not only true that the Hessian of the log mu is negative semi-definite, but its eigenvalues are sandwiched between some beta and alpha, with beta over alpha bounded. Okay. So when you have this condition, you don't have to even think about a clever algorithm, very standard algorithm, similar to gradient descent for optimization, but here a noisy version of that work. I think it's fair to say that in the discrete world, things are not as as well defined. So in the discrete world, let's say you have a distribution on the hypercube you want to sample from. There is really a patchwork of incomparable conditions under which you can sample. Okay. So one of these tools that allow you to sample in the discrete world is sampling via counting. So what do I mean by that? So there are some problems, some very specific problems for which you have some sort of a counting oracle. So what do I mean? You have a hypercube, you have a distribution on the hypercube. You have an oracle that, given the description of a sub-hypercube, it gives you the mass on that sub-hypercube. Okay, so that's what I mean by counting for this talk. And here are some distributions for which we have this good oracle. So let me go through them. So spanning trees is perhaps the most famous one. In the spanning tree case, the distribution you want to sample from is given a graph. You want to sample a uniformly random spanning tree, and we view this as on the hypercube. Let's say n is the number of edges, and +1 indicates presence of the edge in the spanning tree, -1 indicates non-presence. And your mu is putting a mass of 0 on the subsets of edges that are not a spanning tree, and a mass of 1 on the subsets that are a spanning tree. So if you wanted to compute the mass of the entire hypercube, for example, you would be needing to count the total number of spanning trees, and this is doable via the matrix tree theorem. You can write it as the determinant of some Laplacian matrix. Similar thing works for the subhypercubes. So in the sub-hypercubes, you condition on some edges being in or out, but a similar thing holds. So another famous case is planar perfect matchings. Here, your distribution is given a planar graph. You want to sample a uniformly random perfect matching. Again, due to a famous theorem, FKT, you can again write this as the determinant of some matrix. That's easily computable. Another example that's maybe like less familiar is Eulerian tours. So here, the distribution is you're given a directed Eulerian graph, and it has one Eulerian tour, but it could have many. So your goal is to sample one uniformly at random. Because of some theorem that has the best name ever, you can again count this. So this best theorem allows you to write the number of Eulerian tours in such a graph as the number of arborescences times something, and the number of arborescences again you can write as a determinant. So this last one is a little bit more complicated to describe. Let me just describe it briefly, but don't worry if you forget it. So here, this is a determinantal point process. It's described by some n by n matrix, and this n by n matrix gives you a distribution on subsets of 1 through n, where the measure of a subset is proportional to the corresponding principal minor. Okay, so the determinant of the principal minor. You need obviously these principal minors to be non-negative for this to be a distribution. So this happens in two very useful cases. One of them is when this matrix is PSD. Another case is when this matrix is skew symmetric. So in both cases, you get non-negative determinants, and this gives you a distribution. So those are two flavors of determinantal point processes. And again, if you want to, let's say, compute the measure of the entire hypercube, you can just simply do it by computing the determinant of your matrix plus I. You can just expand this out to see that this is the determinant, the sum of all the principal minors. So when you have this useful counting oracle, you can easily translate that to a sampling algorithm. This is the easy side of a well-known equivalence between counting and sampling due to Jerome Veli and Tamazirani. And this is really the easy side, because I'm going to show you what it looks like on half of the next slide. So imagine you want to sample a spanning tree. You have a counting oracle. Here is what you do. You go over the edges one by one. And for each edge, you just compute the marginal of it, conditioned on what you've done in the past. And once you compute the marginal of the first edge, you flip a coin with that marginal and decide whether to keep it or not. And then you just condition on what you've done, and you compute the next marginal and so on. So each of these probabilities is just the ratio of the measure of two sub-hypercubes. The problem with this, sampling algorithm is that it's very sequential. So here I need to know what I've done in the past to know what probability to compute. Right? On the other hand, for all of the problems I showed you on the previous slide, because the count can be reduced to a determinant computation, we have very fast parallel algorithms for them. So here, the notion of parallelism I'm using is this notion NC. You have so think of it as you have polynomially many processors, n to the 100 processors. And your goal is to reduce the time to polylogarithmic. Okay? So Shanky basically showed that anything you do in linear algebra can be parallelized, including computing determinants. So this raises the question of we have good algorithms to compute these marginals. Can we somehow make this process more parallel so that we get parallel sampling algorithms? So so the goal is to sample in parallel. So we want RNC type algorithms. The R just stands for randomized because we have to use randomization in sampling. And the main result I want to show you is that, yes, in most of the examples I showed you, except for this planar perfect matching case, we can do this by going beyond the Boolean hypercube. So interestingly, we had an earlier work where we tried to really stick to the Boolean hypercube, and it seemed impossible to just make it work. But if you move beyond the Boolean hypercube to continuous space to Rn, you can actually make these algorithms happen. All right, so here's the outline of the rest of the talk. I want to tell you what's the connection between discrete and continuous first, without telling you the algorithm, and then I'll tell you what the algorithm looks like. Yeah, so the connection itself is very self-contained, very cute. So there's really like not a lot of things that you can do to go from the hypercube to Rn. One of those things is taking convolutions or making the hypercube or convolving with noise. So that's the thing we are going to do. So so we have this distribution on the hypercube. I'm just going to convolve it with a Gaussian. So add independent Gaussian noise to my samples. And here I've drawn the picture of 3 different convolutions with increasing width of the Gaussian. As you can see, you know, my distribution here is like very jaggedy, and then suddenly here I get a very nice unimodal distribution. It has it no longer has like 2 modes and stuff. So this is really like the main workhorse of our work. We show that for all of those distributions except planar perfect matchings, if you convolve with Gaussians, after the variance of your Gaussian passes a certain constant threshold, you actually get very nice distributions. In fact, log-concave distributions, the kind that are easy for the continuous sampling. So yeah, so this is true for spanning trees, for Eulerian tours, for DPPs, but not true for planar perfect matches. So I want to show you that actually this lemma is very simple. It has a 2-line proof here. If you think about what this convolved distribution is, I've just written the PDF of this convolved distribution here. At a point W, you just sum up the contribution of a Gaussian centered at each x. So this part is coming from the Gaussian, this part is coming from mu. And notice that if I open up this quadratic, so W squared term actually goes away because, sorry, the W squared term, you can factor it out. The X squared term is constant for everything in the hypercube. And then you get this term, which depends on W and X. It's the inner product of W and X, okay? So one thing to note is that these sampling algorithms that we have in the continuous case, they need some sort of access to your distribution. The sort of minimal access that they need to your distribution is for you to be able to tell what the PDF at a particular point is, or up to proportionality what the PDF at a particular point is. And I claim that for all of the discrete distributions mu that I showed you before, we can actually give you this PDF. So if let's say you wanted to compute this PDF at the point, let's say W equals 0, right? This part is easily computable. This part, when W is 0, it's just the sum of mu x over the entire hypercube. That's exactly the counting algorithm that I have, right? When W is not 0, this I claim is a weighted version of your problem. So for example, in the spanning tree case, e to the WC is giving you some positive weights on the edges of your graph. And the weight of a spanning tree is the product of the weights on the edges. And here you're just computing the weighted sum of these spanning trees. And all of those determinant-based counting algorithms actually work under weights. All right, so one good observation here is that you actually do have access to the PDF of this continuous distribution. But you can also see this fact from this simple calculation. If you take the log of this expression and then take the Hessian of this, there are 2 terms. One is coming from this, so minus I over C, plus This part requires a little bit of computation, but this is actually a standard function. This is called the Laplace transform of your mu. And the Hessian of log of this is very well studied, very well known. It's just the covariance of your distribution. I've written it at the point w equals 0, but the similar things hold at other points. So from this calculation, you can see that as I increase c, the width of my Gaussian, at some point, this first term, which is negative, is going to win over the second term, which is positive. And basically, all you need for this thing to become negative semi-definite is that your covariance is not too large.
You said positive words, but okay. Yeah.
So the Hessian of this thing is PSD. The Hessian of this thing is negative semi-definite. There are these two like opposing factors. And yeah, so that's why there is a specific threshold after which this thing becomes log-concavity. All right, cool. So so there is a threshold determined by the maximum eigenvalue of your covariance matrix after which this thing becomes log-concave. And if you go slightly above that threshold, let's say that threshold was C0, but you go to 2C0, you not only get log-concavity, you actually get well-conditioned log-concavity because this really wins over the second term.
What are the entries of this covariance matrix?
Yeah, so the covariance matrix is simply this. It's the expectation of like XX transpose minus expectation of X transpose, where all these expectations are taken when X is sampled from mu. So it's an n by n matrix. Cool. So, all right. So now I have to tell you, so I cheated a little bit. I just computed this Hessian at the point w equals 0. You could ask what happens at other points. So let me show you what happens at other points very quickly. So at other points, you have to deal with weighted versions of your distribution. That's all. Remember, this was like a weighted version of our distribution. So this is what I'm going to call in this talk exponential tilt. Sometimes people call it an external field. When you basically multiply by something that's log linear. So basically, e to the w dot x. That's a factor that you multiply by your distribution. That's another distribution on the hypercube. You can think of it as weighted spanning trees, if spanning trees is the thing that you remember. So yeah, so this is an operation that maps distributions to distributions. So spanning trees become weighted spanning trees. DPPs actually become DPPs with rows and columns of the matrix defining them just scaled. I'm surprised nobody asked this, but Eulerian tours are actually not a distribution on the hypercube. So I'll tell you what happens in the Eulerian tours case later. You have to first somehow make it a distribution on the hypercube, and then you'll see what happens. But the moral of the story is that the class of distributions we are dealing with, they all are somehow connected to determinants. They are all closed under this sort of exponential tilt. So everything is good. Okay. So at any point w, the convolution that I showed you before would be negative semi-definite as long as the covariance matrix of these exponential tilts are bounded. So at w equals 0, you needed the covariance of your original distribution, but at other points you just need the exponential tilts of the distribution. So this condition, surprisingly, has been studied before. This condition is called semi-log concavity in a work of Eldon and Shamir, although they didn't observe that this corresponds to really log concavity of convolution with Gaussians. So the reason we know this condition holds for all of the distributions I showed you is that we actually know something even stronger for them. So there is this framework, spectral independence, that has been very useful for sampling problems in the recent years. And spectral independence really is basically equivalent to this condition that I wrote here. So instead of the covariance of your matrix being bounded by some multiple of the identity, it's bounded by some multiple of its own diagonal. Yeah, people, if you're familiar with, let's say, I don't know, high dimensional expanders or spectral independence, this is really like spectral independence at the link of the empty set, just written in the language of covariances and things that probabilists understand. Yeah, so the diagonal of this covariance matrix has bounded entries. So this is a distribution on the hypercube. So the diagonals of the covariance are always at most 1 because they're just variants of a Boolean random variable. So this is always smaller than this. And everything except planar perfect matchings has this property. Now let me take an interlude and tell you what happens to Eulerian tours. So okay, so to go from to make Eulerian tours workable in this framework, we have to first map it to the hypercube so that we can then map it to beyond the hypercube. So to do that, I have to introduce switching networks. If you were here for Ryan's talks on Monday, you might first see some similarity, but this is really not what I'm going to talk about. Ryan talked about like these baby distributions and baby squares and so on. What I'm going to talk about is really like the giant versions of these babies. Okay, so all right, so Eulerian tours, how do we represent them on the hypercube? So here is the trick. You can actually reduce a general Eulerian graph to one in which the in degrees and out degrees at every vertex are 2. And to do this, you need switching network gadgets. So here is what these gadgets look like. Let's say we have a vertex of degree 3. I'm going to replace it by such a gadget. There are 3 incoming lines corresponding to the 3 incoming edges and 3 outgoing lines. And you just put these like switches in the middle, each time connecting 2 wires. And the way you think of it is, you know, a random switch is happening at these things. And then once you determine a switching network, that gives you a distribution on permutations on the output. So the goal of this gadget is for the permutation on the output to actually be close to uniform on the space of all permutations. So Ryan talked about like ways of generating random permutations that have close like low moments, but here we really want like everything to be close. All right. But once you do these switching network gadgets, now you have a binary choice per vertex because the in degree and out degree are 2. There are only 2 ways to map the incoming edges and to the outgoing edges, like this and this. So now your distribution is like really on +1, -1 to the end. Call one of these +1, call one of them -1. And some subset of +1, -1 to the end gives you Eulerian tour. Some subset gives you like disconnected cycles. So, but even after you do all of these reductions, Boucher showed that there is a determinantal way to write the count of these Eulerian tours. This is actually this is different from the best theorem that I mentioned in the beginning. So Boucher showed that there exists a skew symmetric matrix L such that its principal minors basically tell you whether some particular set of switches give you an Eulerian tour or not. So all of its principal minors are 0 or 1, and you get 1 exactly for Eulerian tour, 0 for non-Eulerian. For people who are familiar with the jargon, this is actually like a delta matrix. So okay, so after you've translated everything to the hypercube, now it makes sense to talk about exponential tilts. So exponential tilts become biased switching networks. So instead of these switches happening with probability 1/2, 1/2, they just happen with probability P1 minus P, where P and 1 minus P, they are like tangent hyperbolic of like these weights. Okay, so how do you construct these switching networks? Let me just briefly mention it. As you might guess, like random switching networks actually work. So if you have degree many incoming wires and degree many outgoing wires, just construct a random one. Each time pick 2 wires, put a switch between them. And if you do this for roughly like degree log degree many, your outputs are close enough to being uniformly random. But because we are able to deal with bias permutations, you don't even have to deal with like approximately uniform permutations. There are networks you can construct with biases of size degree squared that give you exactly uniform permutations. Let me also mention this as a fun like side open problem. If you want to get exactly uniform permutations, as far as I've researched, it's open what is the minimum size you can get here. So just by entropy bounds, you can't go below like degree log degree, but degree squared is the best we know. Cool. So once you replace everything by switching networks, you get a distribution on the hypercube, and you are in the good graces of our framework. All right. So let me summarize this part. I started with telling you that we have some sort of counting oracle that maps sub-hypercubes to measures to the entire measure on that sub-hypercube. And then I pulled the rug and switched this counting oracle with a more sophisticated one that gives you really like the Laplace transform of your distribution. But the observation was that for the distributions we care about, we actually have this more sophisticated version. And the main result that we have is that as long as you have this more sophisticated counting oracle, and your distribution satisfies that all of its covariances are bounded, you get basically this sort of parallel sampling algorithm. You get sampling algorithms that run in polylog time, but slightly worse than polynomial many processors. Quasi-polynomial many processors is what you need, as long as you know that all of your distributions have bounded covariances, or let's say they are spectrally independent on their own. All right. So this condition of being spectrally independent on their exponential tilts also has a name, fractional log concavity, but we know it for all of the distributions I mentioned. Yeah. And also this weaker notion of just the covariances being bounded by I is enough. So this main result gives you a quasi-RNC sampling algorithm for Eulerian tours. It gives you a quasi-RNC sampling for DPPs defined by a skew symmetric matrix. But actually, we tried really hard to remove this quasi from all of these. We were able to do this in this paper for distributions that satisfy something stronger than the covariances being bounded, distributions that I call transport stable. So I'll define transport stability later. It's some property of the distribution. But as long as you have this stronger property, you can change quasi-poly to poly and get like a fully kosher parallel sampling. So this holds for DPPs defined via symmetric PSD matrices. It holds for spanning trees and so on. Okay. Let me mention that this stronger property, it's not that the case that it doesn't hold for these. We actually conjecture that it holds for all of these distributions. We are just not able to prove it for these. After this paper came out, in some ongoing work, we tried to get rid of like this condition and drop the quasi in these two cases too. So it seems like we can do it, but this paper is not out yet. All right, so here is what transport stability means. So remember, we were dealing with like these exponential tilts. So transport stability says that as long as you change the parameter of your tilt by a small amount, your distributions change by a small amount. Okay. And the way I measure the distance between distributions is via Wasserstein distance. So this is how much, so if you want to transport mass, probability mass from this distribution to this distribution, on average, how much in Hamming distance do you have to move? Okay, so that's Wasserstein distance. And as long as it satisfies this inequality, that the transport distance between your distributions is bounded by some constant times the L1 distance between your tilt parameters, I'm going to call that transport stability. And this is a stronger notion than covariances and so on being bounded. I'll show you in the next few slides. As long as you have this, you get to drop the quasi. So for spanning trees and for DPPs and so on, we can show that this holds with C equals 1. One trivial fact is that this holds for any distribution, no matter what, with some worst constant C equals order. Okay. So just to show you like how this is related to earlier stuff, I showed you semi-log concavity was like a condition on the covariance being bounded, but you can actually rewrite this in an equivalent way. So the equivalent way is to say that the means are Lipschitz with respect to the tilt parameters. That's because the covariance is somehow the derivative of the mean. So yeah, so this is the earlier semi-log concavity condition. You just want the means of two tilts in L2 to be bounded by C times the distance in L2 of the tilt parameters. And you might say, okay, so things here are L1, things here are L2. What's the relationship between them? So this condition is actually weaker than the corresponding one for L1. So if you replace both of these 2's by 1, you get a stronger condition. And that's obviously implied by this. So if you have two distributions that are closed in Wasserstein distance, their means are also closed in L1. So that's why like this is like really the strongest of all the conditions. Okay, so let me tell you where this transport stability is coming from. In the case of spanning trees, for example, there is an old theorem of Federer and Mihai that works for spanning trees and DPPs and so on, that tells you how to construct some sort of a coupling between conditionings of the spanning tree distribution. So what does it say formally? So you have your spanning tree distribution, uniformly random spanning trees on a graph. Pick your favorite edge E. So let's say, I don't know, this edge. There exist two random spanning trees, T and T prime. These are not independent random spanning trees. They are dependent, fully dependent, such that when you look at them individually, the first one is uniformly random conditioned on containing this edge. The second one is uniformly random conditioned on not containing this edge. So they always like differ at least on this edge. And they are as close as possible in some sense. So they have to differ on this edge. They must also differ on somewhere else, but that's all. So they always like differ on exactly two edges, as in this picture. So these two spanning trees differ on exactly this edge and this edge. So Federer and Mihai showed that this pair of random variables always exists for spanning trees. It also exists in some other distributions. In our paper, we show some similar statements for distributions that I didn't talk about. So go look at the paper for those. But basically, transport stability, you can get it from statements like this by gluing these couplings. Essentially, if you want to go from one tilt to another tilt, just change the tilt parameters one coordinate at a time and use these couplings every time to construct like low transport distance couplings between the distributions. All right. And I showed you transport stability already implies semi-log concavity. We actually conjecture that the same thing, actually Federer-Mihai statement holds in a similar fashion for Eulerian tours and so on. The difference is in the spanning tree case, when you look at T and T prime, they are one swap away. So they are always like they differ on this edge, but the other edge must go the other way around. So like if this one doesn't include this edge, then this one includes the other edge. In the Eulerian tour case, it's not necessarily a swap, it's a flip. It should be a flip. We also show for some distributions that similar couplings hold for some interesting distributions where you have to use like longer distances. So that's the connection. That's how you go beyond the Boolean hypercube. That's how you go to the continuous case. Now let me show you the sampling algorithm itself. So the sampling algorithm is, as I promised, it's the same thing that diffusion models use and also known as stochastic localization in our community. So here I've written the whole algorithm. So just a quick note about the algorithm. So stochastic localization has been a useful tool for analysis of properties of distributions, but it has also been recently used algorithmically by Eulerian, Montanari, and Selke. So this would be the second algorithmic use of it. The way Eulerian, Montanari, Selke use it is different from our use. I'll tell you the difference in 1 second. But let me first show you the algorithm. So there is this random process that you are constructing little by little. So there is this tilt parameter W that you're changing over time. You start with 0, and the tilt 0 of your distribution is your original distribution. What you do in each step is you sample from some noisy version of your distribution. So you add noise to get a nice distribution, a log-concave distribution. And then you sample from this log-concave distribution. You get some vector in Rn. And then you modify your tilt by basically what you sampled. You add what you sampled to your tilt up to some scaling. So maybe, I don't know, you sampled here, and now you tilt your distribution this way. Okay. But again, the next step, you convolve this with a Gaussian to get a nice smooth distribution. You again sample from it, and then you add whatever you sampled to your tilt, and so on. As you can see, like at least pictorially, this distribution is getting more and more pointy. It formally always like converges. It with probability 1 converges to a point mass as you do this process for a large number of steps. And we actually know the distribution of this tilt parameter exactly at every time step. So this is due to recharacterization of stochastic localization by Eulerian and Montanari. But due to their characterization, we know exactly what the tilt parameter at time t is distributed as. So if you scale it appropriately, you divide it by time, you multiply it by c. It's just another noisy version of your distribution. So your distribution convolved with a Gaussian, but the variance of this Gaussian is going to 0 with time. So as t goes to infinity, you are getting closer and closer to your distribution. So obviously, like when t is infinity, this is good enough as a sample from you. So one observation is you don't have to go to infinity. If you stop this process at roughly log n time, the Gaussian here will have infinity norm bounded by a constant, let's say half. So there are n independent Gaussians, each of variance 1 over log n. So the maximum of them will be 1/2 with high probability. So then the sign of a +1 minus vector with something of L infinity norm bounded by half is the same as the original +1 minus 1 vector. So you can just round the sample you have here, just look at the signs. And the +1 minus 1 vector you get is in TV distance close to your distribution. All right, all right, so let me come back to this. So the way we are running basically stochastic localization is a faithful simulation of stochastic localization up to how you do this step. The version that Eulerian, Montanari, and Selke use is, instead of sampling from a distribution like this, which is complicated in some cases, they just basically compute the mean of this distribution and replace the entire distribution by like a point mass at the mean. So that introduces some approximation errors, but in their case, like they can tolerate it. So that's why I'm saying this is a different discretization. Cool. Okay. So, all right. So one thing that I haven't shown you so far is there is this continuous distribution. We know it's log concave, but how do we actually sample from it in parallel? Right. Yeah, going very fast. Okay. So this is actually an open question in the continuous sampling community. So you have a continuous distribution. It's well-conditioned log concave. How many times do you have to query, let's say, the density of your function or its gradients or its like low order derivatives before you can output a sample? Okay, so this is the minimal number that you need. The minimal number of these queries that you need is open. You could feasibly have an algorithm that only queries polylog n many such things. And then you don't even need to care about like parallelization. It's just enough. But so far, we don't know of any algorithm like this. In fact, there are some people who are trying to prove impossibility of this. Fortunately, though, parallel sampling in polylog n time is not open. So there is this work of Shen and Li that we use as a black box that gives you samples. But let me tell you like the idea that goes behind these sorts of algorithms at least. There is also like in our ongoing work, we use basically the same parallelization idea to a different sampling algorithm. What goes in parallelizing like sampling algorithms that you might be familiar with is you always have some sort of a stochastic differential equation that you have discretized. Here I've written like the discretization of Langevin dynamics. So what does it say? It's like a noisy version of gradient descent. You move from a point xt to a point xt plus dt by just moving a little bit in the direction of the gradient of your log density. So that's similar to gradient descent, but you also add noise. All right, so this is very sequential because you have to go from xt to x plus t to xt plus dt and then to xt plus 2 dt and so on. But there is this general idea you can use called Picard iterations to parallelize all sorts of algorithms like this. The idea is think of basically like turn this like sequential like thing into a fixed point problem and then iterate. So what do I mean by that? So imagine you have a trajectory of these points, initially like started at a random guess or something, like some arbitrary guess. What I can do is I can compute the gradients of log density at my current trajectory and use those to get a new trajectory like this. Right? So xt I minus 1 is my trajectory at iteration I minus 1. I compute all of these things in parallel, and then I just like compute the prefix sums of them to get a new trajectory xti. So this is an operation that maps a trajectory to a trajectory. It's called Picard iteration. And this thing, you can actually just iterate polylog times, and it will converge to the fixed point of this operation, which would be a solution of this. So Shen and Li basically use a similar idea, but to a different algorithm. It's not the Langevin dynamics, but in our ongoing work, we should even for Langevin dynamics basically. Cool. All right. So that's basically the gist of the algorithm. Now you can just piece it together with the previous framework to get your algorithm. Now let me go back to transport stability and tell you why we got the two different results, quasi with the quasi and without the quasi. So the reason is very subtle, but this is the last slide. Okay, so the point is these continuous sampling algorithms, they come with approximate sampling guarantees. So the point they produce for you is not it's never a true sample from your distribution. It's always approximately from your distribution. So really, like the devil is in the details. So what kind of approximation guarantee do you have? So in the work of Shen and Li, the approximation guarantee they have is that you get some point that is you get a sample from a distribution that's in Wasserstein distance close to your distribution. And because these W's that you sample are tilts of future steps, you need to tolerate like a change in the tilt parameter. And so transport stability is able to tolerate those kinds of errors. So basically, if you know that in some step your distributions have epsilon Wasserstein error, every iteration from that point on, that epsilon gets multiplied by a c. If you know C is transport stability. Okay, so for spanning trees and so on, every step your error gets multiplied by a constant, but you only have log n of those steps. So the errors in the beginning get multiplied by only a polynomial factor. So it's enough to start with an inverse polynomially small error. In general, for general distributions, you can only say that the errors get multiplied by O of n every step. And so after log n steps, they get multiplied by n to the log n. So that's why you need to start with an inverse quasi-polynomial error. So that's all there is to that difference. And basically, in our ongoing work, the way we get around this issue is by giving parallel samplers that don't give you Wasserstein accuracy, but give you TV distance accuracy. So TV distance accuracy doesn't have this problem that it blows up over time. Cool. So let me conclude. So I showed you some algorithms for some way of using stochastic localization to get parallel sampling algorithms. There are some open problems here. So planar perfect matchings is the case that we didn't solve. But more generally, these are wide open questions. As far as I know, the answer to them should be yes. So I used some assumptions on the distribution, like I don't know, spectral independence or semi-log concavity and so on. But what is the complexity for arbitrary distributions of sampling given oracle access to the Laplace transform or oracle access to the subcube counting thing? If you're interested, I can even give you like candidate algorithms that I think should work in parallel here, but we're just not able to analyze. Thank you.
Questions for Nima?
If I remember correctly, this Eulerian calculus, how they get a Bassett error, whereas you get a TB error. What's the need for the difference?
Good.
It's
a what?
No, you said something how you update.
So there are two issues. Okay, so since you mentioned the work of Eulerian, Montanari, and Selke, in their work, they study sampling from the Sherrington-Kirkpatrick model, if you know what that is. So the issue is, and they get a worse guarantee they get a worse than TV distance guarantee than for their sampling algorithm. So there is a fundamental reason they can't get TV distance guarantee. The reason is we had like this clean given counting oracles. In their work, they only have approximate counting oracles. So essentially, like the continuous distribution, like even if you wanted to like plug that distribution into our framework, you would only have access to, let's say, approximate PDFs of those continuous distributions. So with those approximate accesses, you just don't get, you can never get rid of the Wasserstein distance. Another reason Wasserstein distance shows up is because they are using like a different discretization, but in their case, because they have to get a Wasserstein distance error, it's like, why not use just discretization? This is actually previous work.
Oh, and the other work.
You mean this thing or?
The other.
So this is okay. This one. So this is like so this is like a mathematical process. This is not formally an algorithm. You have to like plug in something for here to get an algorithm. But this mathematical process here, they just use it in some analysis as some analysis technique, and they show that like if you do this like accurately at every step, the distribution of WT you get is something like this. This is a mathematical statement. Sorry, what was the question again?
Because you said that the first part basically converges your distribution to like a point mass, right?
Yes, so that's actually easy to see once you know this characterization. So if you give me like a distribution, if you give me a W that's distributed like this for a very, very large T, you put T times that as your external field. So then it's converging to something that's like infinitely large. And so like it's very easy to see that just like puts the entire mass of your distribution on whatever was your sample from here. I don't know if that answers the question. So you can make this algorithm a little bit more complicated by not just rounding the tilt parameter, but actually like computing what this distribution is for a large T, and then looking at what point mass it's close to, and then taking that sample. But these are like formally close to each other.
Yeah, that's what the algorithm relies on sample from convolution distribution with the Gaussian distribution.
Yes.
Do we have a good understanding on like what kind of distributions actually are easy to sample from after convolve with Gaussian? A lot of distributions, I think, in a continuous distribution, if one system convolve with Gaussian, it's actually very difficult to sample from.
Yes, that's a good point. So if you start with a continuous distribution, you have to have some sort of a counting oracle corresponding to like integrating your function under a Gaussian measure, which is pretty hard to do. But yeah, I don't have a good answer except for like the distributions here. Also, like yeah, in general, in the discrete case, many times you have not just determinant-based counting, but you have other counting algorithms that are, let's say, not based on Markov chains. So like deterministic counting algorithms, such as the ones given based on the Barbanak's method and so on. So all of those would give you actually parallelizable counting algorithms. The difference is they're approximate. But up to that small difference, for all of those, convolving with Gaussians is also like easy.
What makes planar perfect matchings hard?
Good question. So here is the hard case. Let's say your entire graph is just a giant cycle. So this has two perfect matchings, the odd edges and the even edges. So then your distribution is like half-half on two opposite ends of the hypercube, right? So if this is the hypercube, there, like your distribution would be a Boolean distribution, just a half-half distribution of these 2 points. Then you can easily see that if you put like Gaussians on top of these, the distance of these 2 points is very large. So you have to put very wide Gaussians for them to reach each other. And yeah, that's kind of the intuition. Like for spanning trees, things are actually close to each other. We know from combinatorics that you can move in the space of spanning trees by just doing local changes. And that's basically the intuition of why putting small Gaussians on top of spanning trees gives you a log-concavity distribution.
In the algorithm you presented, what do you do if I equals 0?
W is 0 is 0. This one? Or?
No, the next algorithm.
The parallel sampling algorithm. It's actually a good. Okay, so that's a good question. You actually have to start this from somewhere close to the mode of your distribution, but the mode is easy to find using gradient descent. So you just start from like the constant trajectory near the mode.
on the previous slide, stochastic optimization. Cosmetically, this looks a lot like the polarization step in fractional.
I've heard that comment from many people.
Okay, is that just a surface level thing, or?
I just don't know. Yeah, to me it looks a coincidence, but yeah, maybe there's deeper correction.
Check multiplicative ways. To check many different receptors. You choose.
Oh yeah, what I meant was so in the spanning tree case, this is what we have. So in the translated to the hypercube language, you can have two vectors x and y, two random vectors x and y in plus 1 minus 1 to the n, such that x minus y is always, so you fix your favorite coordinate I, so fix I. So you can make sure that this is always EI minus EJ for some J. So that's equivalent to what I wrote. In the Eulerian tour case, what you need is not this. It could also be the case that x minus y is, so basically in the Eulerian tour case, you have to put a plus here. So it could be like either like you swap a minus to a plus or a plus to a minus. So that's what we conjecture should hold for evaluators. We can't prove it, but we can prove similar statements for more complicated distributions. There are some distributions for which you can prove this difference is like found in normal.
Okay, let's take any further questions offline. So let's thank Nima again. And we'll return in 30 minutes.